the probability of E by F is already occurred is given by 1 by 4. If LHS is not equal to RHS, then they are not independent event. The quadron is an AS, so the probability of F is 4 by 52, that is 1 by 13. Hello dear students, welcome to this session of mathematics class. I am Mr. Niranjan, faculty of mathematics, Vidhyaashram PU College, the Temple of Excellence. Now in this session I am going to discuss regarding the independent event and the problems based on an independent event. Now independent event. So when did you say an event is said to be independent? Suppose E and F are any two events, the probability of one does not depend upon the probability of the other one. That is, the occurrence of one does not depend upon the occurrence of other. Such events are called independent events, that we will discuss now today with an example. Consider an example. Consider the experiment of drawing a card from a deck of 52 playing cards. Consider the experiment of drawing a card from the deck of 52 cards in which the elementary events are assumed to be equally likely events. Let us define the two events E and F. Let us define E and F as the two events, that is, the card drawn is a spade and the card drawn is an ace. Let us define an event E such that the card drawn is a spade and for F the card drawn is ace. Now, since in a deck of 52 cards, the probability of getting E is nothing but the spade. The card drawn is spade. Probability of E is 13 by 52, that is 1 by 4. Similarly, the probability of getting an ace is P of F is equal to 4 by 52, that's equal to 1 by 13. So, E is an event that the card drawn is a spade. So, therefore, the probability of E is P of E is equal to 13 divided by 52, that is 1 by 4, and F is an event, the card drawn is an ace, so the probability of F is 4 by 52, that is 1 by 13. That means here E and F is nothing but the event, the card drawn is ace and the spade is given by E intersection F is equal to 1 divided by 52. Hence, by the property from the theorem, the probability of E by F is already occurred, is given by probability of E and F, E intersection F divided by the probability of F. Probability of E intersection F is 1 by 52 divided by probability of F is 1 by 13. 13 4s gets cancelled, this is 1 by 4. So, the probability of E by F is already occurred is given by 1 by 4. Now, let us come to the second part. So, since probability of E is 1 by 4, which is also equal to probability of E by F. Probability of E is 1 by 4. This is also equal to probability of E by F. We can say that the occurrence of the event F has not affected by the probability of the occurrence of the event E. Here, the probability of E is 1 by 4. That is also equal to probability of E by F. That is, F is already occurred. From this, we can conclude that the occurrence of an event F, has not affect the probability of the occurrence of the event E. So, therefore, we have the probability of F by E. Let us discuss the probability of F by E. E is already occurred is given by probability of E intersection F by probability of E. That is, probability of E and F is 1 by 52 and the probability of E is equal to 1 by 4. That's equal to 1 by 13. That is equal to the probability of F. So, in the first case, probability of E by F is equal to 1 by 4. That is equal to probability of E. In the second case, the probability of F by E is equal to 1 by 13. That is equal to probability of F. That means, here the probability of F is equal to 1 by 13, that is probability of F by E, that is E is already occurred. This shows that the occurrence of an event does not affect the probability of occurrence of the event F. That means, in the previous case, the occurrence of F does not depend upon the occurrence of F, or similarly the occurrence of F will not affect the occurrence of E. So thus E and F are said to be E and F are two events such that the probability of occurrence of one does not depends upon the probability of occurrence of the other, or the probability of occurrence of one will not affect the probability of occurrence of the other. Such events are called independent events. That means the occurrence of one does not affect the occurrence of the other. The probability of occurrence of one does not depends upon the probability of occurrence of other. Such events are called as an independent event. So it does independent means it does not depends upon any occurrence. It is independent. So the probability of occurrence of one does not depends upon the probability of occurrence of other is called an independent event. So this is nothing but an independent event. Now let us come to the final conclusion. Two events E and F are said to be independent. Two events E and F are said to be independent if and only if the probability of F by E is equal to probability of F, provided probability of E is not equal to 0, and similarly the probability of E by F is equal to probability of provided P of F is not equal to 0. That means the probability of F by E is already occurred is equal to probability of F, and probability of F by F is already occurred is equal to probability of E. Then by the multiplicative theorem on probability, we can say that probability of E intersection F is equal to probability of E into probability of F by E. And similarly, if E and F are independent events, then this equation 1 can be written as probability of E intersection F is equal to probability of E into, since probability of F by E is also equal to probability of F. So therefore, from 1 and 2 we can say that probability of E intersection F is equal to probability of E into probability of F. This is called an independent event. So then the events E and F are said to be independent events. So therefore, the probability of E intersection F is equal to the probability of E into probability of F. If this condition is satisfied, then the two events E and F are said to be independent events. That is called independent events. So if E and F are any two events, then the probability of occurrence of one does not depends upon the occurrence of other. That is probability of E intersection F is equal to probability of E into probability of F. Then two events are said to be independent events. They are called independent events. So the final formula to verify whether the events are independent or not, we are going to use this probability of E intersection F is equal to probability of E into probability of F. Now let us write down the formula for this. That is, in general, let E and F be the two events associated with a sample with the same random experiment. Then E and F are said to be independent if and only if the probability of E intersection F is equal to probability of E into probability of F. The probability of E and F is equal to probability of E into probability of F. Now let us discuss with a small example. Let us consider an example. Let E and F be the two independent events associated with a sample same random experiment. Then the given, what is given, probability of E is equal to, given that probability of E is 3 by 5 and the probability of F is equal to 1 by 5. So if E and F are independent events, then find out the value of this probability of E intersection F is equal to, let us find out what is the probability of this. So probability of E intersection F is equal to probability of E into probability of F, because since E and F are two independent events. So therefore, the probability of E and F is equal to probability of E is 3 by 5 into probability of F is 1 by 5, that's equal to 3 by 25. So 3 by 25 is the probability of E and F in case of this independent event. Okay. So here What is given? Probability of E is 3 by 5 and the probability of F is 1 by 5. Now to find the probability of E and F, since the given condition is E and F are said to are two independent events. So for two independent events, the probability of E and F is equal to probability of E into probability of F. So therefore, probability of E is 3 by 5 into probability of F is 1 by 5, that's equal to 3 by 25 is the probability of E intersection F, that is E and F. Okay, hope you followed. Now, let us come to the next problem. Let us consider two events. Suppose the two events E and F are said to be dependent if they are not independent. That is, probability of E and F is not equal to probability of E into probability of F. If LHS and RHS are not equal, they are not independent. So they are said to be dependent. Now let us consider an example. Let E and F be the two events associated with a random experiment. Then what is given? Probability of E is 3 by 5 and the probability of F is 3 by 10 and the probability of E intersection F is 1 by 5. Verify whether E and F are independent events or not. What is given? Given probability of E is 3 by 5 and the probability of F is equal to 3 by 10 and the probability of E and F is also given, that's equal to 1 by 5. Now verify whether E and F are independent events or not. Now let us write down the formula for, now we know this, probability of E and F is equal to probability of E into probability of F. Now what is E and F? This is given 1 over 5 is equal to probability of E is 3 by 5 into probability of F is 3 by 10. So this is equal to 3 3s are 9 divided by 50. 9 by 50. So this is not equal. 1 over 5 is not equal to 3 by 50. So therefore, E and F are not, they are not independent events. Independent events. E and F are not independent events. Okay. If LHS is not equal to RHS, then they are not independent events. So hope you followed. So two events E and F are said to be independent events if probability of E intersection F is equal to probability of E into probability of F. Two events E and F are said to be dependent, that is, they are not independent events if probability of E intersection F is not equal to probability of E into probability. So this is an example for an not an independent event, and the previous one, this is an example for an independent event, and this is an example for it is not an independent event. Hope you got an idea. That's all regarding the independent and not independent events. Now let us discuss few more problems based on this. Now let us come to this problem. A die is thrown, so we are going to throw a die. If E is the event, the number appears is a multiple of 3. The number appears is a multiple of 3, and F be the event that the number appears is an even. So the first condition is the multiple of 3. Multiple of 3 means 3 and 6. Okay, multiple of 3 are 3, 3 and 6. Then F is an event that the number appearing is an even number. So the even numbers are 2, 4 and 6. Then find whether E and F are independent events or not. That's all. Okay, very important problem. Now let us see. Now what is given? So here a die, the sample space S contains 1, 2, 3, 4, 5 and 6. Now let us define an event. E is an event. E is the event that a number appear is a multiple of 3. Multiple of 3 is nothing but 3, 6. And F is defined to be an event. F is defined that the number appearing is an even. Even number means 2, 4 and 6. Now what is N? The sample space N of S is equal to 6. N of E is equal to 2 and N of F is equal to 3. Write down the probability. Now in this, the intersection, find out the common. E and F is equal to E and F. So in this, the common element is 6. So therefore N of E intersection F is equal to 1. Now write down the probabilities. Okay, listen. The sample space, let the sample space S is equal to 1, 2, 3, 4, 5, 6. Therefore, N of S is equal to 6. And E is an event that the number appear is a multiple of 3 means 3, 6. E is equal to 3 and 6. N of E is equal to 2. And F is an event that the number appear is an even number. So, the even numbers are 2, 4 and 6. Sample space contains 1, 2, 3, 4, 5, 6 numbers. And E is an event which is a multiple of 3, 3 and 6. And F is an event which are even numbers 2, 4 and 6. And the common E and F is nothing but 6. E intersection F is equal to 6. Now write down the probability. Probability of E is equal to 3 divided by N of E by N of E. N of E divided by N of S, that is nothing but 2 divided by 6. 2 divided by 6, that's equal to 1 by 3. Probability of F is equal to N of F divided by N of S. What is N of F? 3 divided by 6. This is equal to 1 by 2. Now, probability of E and F intersection F is equal to this N of E intersection F by N of S is 1 over 6. Now, write down this probability of E intersection F is equal to probability of E into probability of F. Verify whether these two are equal. What is the probability of E and F? E and F is 1 over 6 is equal to probability of E is 1 by 3 into probability of F is 1 by 2. This is 1 by 6. So, 1 over 6 is equal to 1 over 6. That means, therefore, probability of E and F is equal to probability of E into probability of F. That is 1 over 6 is equal to 1 over 6. Therefore, E and F are said to be independent events. It does not depend upon the others. So, this is an example for an independent event. See, very simple for 3 marks and very easiest problem. Listen, a die is thrown. E is an event. The number appear is a multiple of 3 and F is an event. The number appear is an event. Then find whether E and F are independent event. Now, the sample space S contains 1, 2, 3, 4, 5, 6. Therefore, N of S is equal to 6. E is an event that it is a multiple of 3, 3 and 6. So, N of E is equal to 2. And F is an event that it is an even number 2, 4 and 6. Therefore, N of F is equal to 3. Now, therefore, the common E intersection F is equal to 6. E intersection F is 6. Now, the probability of E is N of E by N of S is 2 by 6 is 1 by 3. The probability of F is N of F by S is 3 by 6 is 1 over 2. And the probability of intersection F is 1 by 6. Now, therefore, what is to prove is probability of E intersection F is equal to probability of E into probability of F. That is, probability of intersection F is 1 by 6 is equal to 1 over 3 into 1 over 2 is 1 by 6. So, E intersection F is equal to probability of E into probability of F. Therefore, E and F are said to be independent events. Now, let us come to the next problem. What is the next problem? An unbiased die is thrown twice. So, an unbiased die is thrown twice. Then, let the event A be an odd number on the first throw and B is an event that odd number on the second throw. So, for the first throw also odd number, for the second throw is also an odd number. Then, check the independence of the events A and B. So, we have to verify whether the events A and B are independent or not. Now, a unbiased die is thrown twice. Let the event A be an odd number on the first throw and B be the event an odd number on the second throw. Check the independence of the events C and B. So, to verify whether probability of A intersection B, A and B is equal to probability of A into probability of B. Okay. Now, let us solve this. Here, an unbiased die is thrown twice. So, if it throw two times, what is the sample space? In sample space, we have 36. N of S is equal to 36. Okay. That is, if all the 36 events are considered to be equally likely events, then we have N of S is equal to 36. Now, what is the conditions given? A and B are the two events defined. A is nothing but the odd number on the first throw, and B is again an odd number on the second throw. Okay. Now, therefore, the probability of A and B can be written as probability of A is equal to 18 divided by 36, that's equal to 1 by 2. Similarly, second throw is also an odd number. Therefore, the probability of B is 18 by 36, that is also equal to 1 by 2. So, probability of A is 1 by 2 and the probability of B is also equal to 1 by 2. The probability of A intersection B, A and B, is nothing but the probability of A and B is nothing but probability of odd number on both the throws. The probability of A and B is nothing but the probability of odd number on the both throws is given by the probability of A intersection B is equal to, that is nothing but 9 divided by 36. 9 divided by 36. Okay. Probability of A and B, that is odd number on the both the throws, are given by probability of A intersection B, that is 9 by 36. This is nothing but 1 by 4. Now, verify whether these events A and B are independent or not. Now, let us verify probability of A intersection B is equal to probability of A into probability of B. What is A and B? This is 1 by 4 is equal to probability of A is 1 by 2, probability of B is also equal to 1 by 2, which implies 1 by 4 is equal to 1 by 2. 1 by 4 is equal to 1 by 4. Probability of A intersection B is equal to probability of A into probability of B. That is 1 by 4 is equal to 1 by 4. Therefore, A and B are independent events. So, A and B are independent events. Hope you followed this. Very simple. See, an unbiased die is thrown twice, then the number of possibilities are 6 into 6 is 36. So, a odd number on the first throw and again odd number on the second throw is denoted as probability of A is 18 by 36, 1 by 2. Again on odd number on the next throw is probability of B is 18 by 36 and the value is 1 by 2 and 1 by 2. Since probability of A intersection B, A and B is nothing but odd number on both the throws is given by 9 by 36, that's equal to 1 by 4. Now verify whether A intersection B is equal to probability of A into probability of B, that is 1 by 4 is equal to 1 by 2 into 1 by 2, 1 by 4 is equal to 1 by 4. So hence A and B are independent events. That's it. Hope you followed. Now let us come to the next problem. This very important problem. 3 coins. So we are going to toss 3 coins are tossed simultaneously. Consider the event E, 3 heads or 3 tails, F at least 2 heads and G at most 2 heads of the pairs EF, EG and FG, which are independent, which are dependent. Now verify whether which are independent, which one of these pairs are independent and which are dependent. Now we have to verify whether it is independent or dependent. Now let us write down the solution. Now the sample space contains, the sample space of the experiment is given by S is equal to, if you toss a 3 coin, if you are going to toss 3 coins, then what is the probability we are going to get is 2 into 2 into 2, 2 to the 4 to the 8. So the sample space N of S contains 8 events like this. First head, 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 tile, head, tile, head, tile, head, 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 tile, 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 head, tile, 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 head and tile, tile, tile. So totally 1, 2, 3, 4, 5, 6, 7, 8. So the sample space contains 8 events. N of S is equal to 8. Now what is the first condition? E, 3 heads or 3 tails. 3 heads or 3 tails means all the 3 tosses are head, head, head or tile, tile, tile. So the possibility is E is equal to H, H, H or T, T, T. So therefore N of E is equal to, there are only 2 events. Okay, now the second, F at least two heads. At least two heads means F is equal to at least there should be minimum two heads. Head, 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 tile, head, tile, head, tile, head, head. So here N of F is equal to N of F is equal to 1, 2, 3, 4. Number of possibilities are 4 events. What is the third? At most two heads. At most two heads. So G is equal to at most two heads. Maximum are 2. So HH, HTH, THH, THTT, THT, TTH and TTT. Okay, so here this contains 1, 2, 3, 4, 5, 6, 7. So N of G is equal to 7. Right. Now, E intersection F, E and F, the common in E and F. What is the common in E and F is E contains HHH, TTT and F contains HHH, HTT, HTH, and so the common in these two is these two are the common. So E intersection F is equal to HHH. So therefore N of E and F is equal to 1. Similarly, the intersection of E and G, E and G. So E contains HHH, whereas G it doesn't contain all the head, because what is the condition? At most two head, at most, maximum two head. There should not be more than 2 or may not be. Now, so the common is TTT. So this is the common. So E intersection G, N of E intersection G is equal to 1. Next, F and G. The common between F and G is, what are the common events? That is HHT. We have HHT, HHT, HHT here. It is first one. HTH, HTH, the second one, and THH. This is the common. So therefore, N of F intersection G is equal to 3. So these are the values of N of E, N of F, N of G, N of E intersection F, N of E intersection G, and N of F intersection G. Hope you followed. Now, let us verify what is to find of the pairs E and F, E and G, and F and G, which are independent. Now, verify whether they are independent or not. So, verify whether these three are independent or not. Now, let us define, let us solve one by one. First one is probability of E intersection F. So, this is equal to probability of E into probability of F. Check whether E and F are independent or not. Now, what is N of E intersection F? This is 1 divided by 8 is equal to probability of E is 2 by 8 and 2 divided by 8 into 4 divided by 8. This is 1 over 8 is equal to, so this is nothing but 4 2s are 8, we will get 1 over 8. So therefore, probability of E intersection F is equal to probability of E into probability of F. Therefore, E and F are independent events. Independent events. E and F are independent events. So the first one is an independent event. Okay. Now let us come to the second part. What is find E and F, E and G. Now come to the second one. Probability of E intersection G is equal to probability of E into probability of G. Verify whether LHS is equal to RHS. E intersection G. What is the intersection G? 1 divided by 8 is equal to probability of E is 2 by 8 into probability of G. What is the probability of G? 7 by 8. So this is 7 2s are 14 divided by 8 8s are 64. So this is equal to 7 divided by 32. So they are not equal. Therefore, probability of E intersection G is not equal to probability of E into probability of G. So therefore E and G are not independent events. E and G are not independent events. Similarly, the last is F and G. Probability of F and G. Verify. Now the third one, probability of F intersection G is equal to probability of F into probability of G. Now what is F intersection G? We have F intersection G is 3 by 8. 3 by 8 is equal to probability of F. Probability of F is 4 by 8 into probability of G. What is G? We have probability of G 7 by 8. So this is 4 2s gets cancelled. 3 by 8 is equal to 7 by 16. This is also not equal. So therefore, probability of F intersection G is not equal to probability of F into probability of G. Therefore, they are not independent. They are not independent events. That means, therefore, F and G are not independent events. So, only first one, E intersection F. So, probability of E intersection F, this is only independent event, whereas the probability of E intersection G, this is not independent, and the probability of F intersection G, this is also not an independent event. So, of the given problem, this pair E and F is only the independent events, whereas FG and FE are, they are not independent, they are dependent events. That's it. Okay, hope you followed this. Among these three pairs, only E intersection F, E and F are independent events, whereas E and G and F and G are not independent, they are dependent events. So that's regarding which are independent and which are not which are dependent. So that's regarding this problem is concerned. Hope you followed this. That's all for today's session. Let us meet with a different concept in the next class. Thank you very much.